All right, differential geometry question. So
Okay.
I think I get geodesic curvature pretty well, and I understand the idea of torsion pretty well.
Okay.
But I don't have any real intuition for what geodesic torsion is. And I remember it came up on a couple problems. I don't remember if we kind of like explained it in class, but
Okay, you're talking about the Frenet frame formulas.
yes.
Okay, so I only know two things, and that is the curvature and the torsion, right? So we have T prime of S equals, right? And then, what is it, N prime of S, and then B prime of S. So, you know, you might get a Frenet frame problem on the final exam, perhaps. You know, I would definitely know more than one, be the 0 or 1. And you remember that everything can be expressed in terms of T, N, and B. And so this is kappa N, and this therefore is minus kappa T. And then this is a plus the torsion here, I think, right? Times B, and therefore this is minus the torsion here times N. Is this correct? Does that look right to you guys? Okay, it's an anti-symmetric set of coefficients here, right? Minus KK, T minus T. Or tau minus tau. And so the only two things I know or it's the curvature here and then the torsion there. Now you refer to geodesic torsion.
Mm-hmm.
And okay, I think, okay, so now this is just for a curve in R3, right?
Right.
Okay, now if you're on a surface, let's just draw a line here. Then we have a different notion, right? Because we have a different set of a different frame, right?
Mm-hmm.
And I think I'm already answering your question that this is not going to be on the final exam because I can't quite remember what these things are exactly,
Okay,
right?
okay.
But of course I know what geodesic curvature is, right?
Right.
The different way of, what is geodesic curvature? Well, we're looking at, let's say again we have a curve here, which is beta of S. Then, of course, the beta prime of S is what let's say it's unit speed, right? So T here is equal to beta prime of S. And then when we look at what is T prime of S, which by the way, T prime of S is beta double prime, right?
Mm-hmm.
So this equals beta double prime of S, right? And then, so it's kind of analogous to this first formula here. Then we don't define this N in the same way because the natural frame over here is actually T. And then we have U, which is a unit normal vector, which is normal to the, as length 1, this is the U, and it's defined everywhere on the surface, right? And then, of course, we have U cross T, right? So this is our natural orthonormal frame. And so this beta double prime of S is equal to, there's the component that the ant controls and the component that the ant doesn't control. Now the key point is, remember our trick, T prime of S, since it has length 1 everywhere, it's going to be perpendicular to T. So there's no T component. Right, so there's just going to be U and U cross T components. And the U component is the normal curvature. You can say capital K times U, and then the geodesic curvature is the component in the U cross T component. And so that's the analogous formula, right? Now you refer to geodesic torsion. Is that where we're looking at the rate of change? We're looking at the rate of change of this frame here, looking at U prime and U cross T prime, things like this.
Yeah.
Okay, so I have to say I don't really remember much about that, but let's go ahead and play that game. But you say you had a homework problem on this. So this is beta double prime of S here. I'll just erase this as KU.
Or even like, it's not super relevant to the final. Like the homework question was about sort of developing this natural Frenet frame. And
Here or the second one?
yeah, well, they call it T, V, and U, but yeah, it's the same thing as what you're doing.
Okay. They call this V here.
Yeah.
Okay.
And I just kind of struggled with it. Like I understood that T is the same, so it's kind of just a rotation about T in terms of like.
Well, let me rediscover it myself here real quick. Okay.
I think that would be helpful.
So let's think it through, right? So if what's still true? What's still true is the only thing that's different is we're defining the frame differently, right?
Yeah.
But the coefficients, for example, still have to be anti-symmetric by that same trick, right? Because the point is that T dot n equals a constant here. It's either 0, right? T dot n is 0 and T dot t is 1. So any of these vectors, any of the other vectors is either 0 or 1. In both cases, they're constant. So we can use that trick to say we have these anti-symmetric coefficients there, right? And so we're still going to get anti-symmetric coefficients here. So this must be minus k. Here is this coefficient, and minus geodesic curvature here. And now our order here is tu and u cross t, right? Tu and u cross t. So this is going to be the t term here, and this is going to be the t term here. And then we have to have zeros along the diagonal, right? Tu and what? This is v, right? And then t, u, and v, right? And so we're going to have zeros. So the only term that's left then is this term here and this term here, right? And unfortunately, my picture is right there, right? So let me just modify the picture. Okay, so there's this one other term here, which is we have a u cross t term here, and we have to call that something. Is that the geodesic torsion? I mean, I would just make a guess that it is. I mean,
Yes, it is.
okay, so what letter do they use? Like tau sub g?
Yeah, it has some G.
I think they define it as negative.
Is this negative here?
I'm pretty sure.
Okay.
Oh, never mind.
There it's, no, there it's positive.
Positive, okay, just to be analogous to that.
Yep.
And then this is minus the geodesic torsion here.
Mhm.
It's kind of coming back to me vaguely, yeah, okay.
You got it.
I mean, you can see how it's sort of analogous, right? I mean, we're defining it. You see, the whole reason there's a zero here is by definition, right? The zero there is because we're defining n to be in the direction of t prime of s. Why not? We'll keep the first formula as simple as possible, right? But then we're not doing that, so that's why we get. That's why this is 0. But here it's not going to be 0, and so we get this sort of this term here is kind of split up into two terms, right? We got the curvature in the direction of u and the direction of u cross t, and then we got the anti-symmetry. So really the only difference is that this term here doesn't have to be 0 anymore,
Right. Okay.
right? And so then okay, I guess we'll call that geodesic torsion. Why not? Because it's just an analogy to this, right?
Huh.
I had figured out. Thank you.
Okay.
Awesome.
So, okay, and does this answer everybody's question? And I had completely forgotten this, but yeah, it makes sense, doesn't it? Okay. So yeah, what is the geodesic torsion like? What does it represent physically? Like
Yeah.
here, okay, that's a reasonable question,
Mhm.
right?
Mhm.
Okay, let's go back to something I actually remember. Torsion. All right, what does torsion mean? Well, I know that's a torsion 0, then you're a planar curve. Remember that theorem? You stay in a plane. So know the proof of that. Know the proof of that theorem. Now, so I would, and then by the way, that's really my understanding. I just have that theorem that if this torsion is 0, then you stay in a plane, right? Okay, well, suppose this torsion is 0. What does that mean? Okay, well, I mean, I guess that's a question we could ask, right? Okay, so it means that, what does it mean?
Change in U is only in the tangent direction.
Change in u, right. You're just in the t direction. What would that mean?
Does it mean it's locally, like, flat?
I mean, here's how I'm interpreting it in my head right now, okay? Because there's one thing that's different here. Is here, see, here you get to really choose both. You see, if you're flying, if you're a fly in 3 dimensions, I can. There's how much I turn left and right, but also up and down, right? So I have 2 degrees of freedom for my unit speed curve,
Right.
And so, and there you go. There's 2 degrees of freedom. So you can specify any kappa, any tau, and you get a curve, right? But here we're restricted to a surface, right? And so if you're saying walk at unit speed, I only have 1 degree of freedom, which is you want to curve to the left, you want to curve to the right, right? That's it. And so that means this is determined, right? This is not something you get to choose. This is something that you measure, right? You get to choose your geodesic curvature. But let's suppose I choose my geodesic curvature. I got that set, right? and then I'm following a certain path. Maybe it's 0. Maybe I'm just trying to go straight, for example. And then what does it mean then for this to be 0? It means that u prime, the rate of change of my normal vector, right, which is pointing straight up. Let's say that I'm the ant walking on the potato, and here's the ground right here, right? Then it's saying that u prime equals t. In other words, if the ground curves down and away from me, right, then my u prime, which is that, goes in the direction I'm going, right? So the extent that the ground curves away from me, I'm just going downhill, fine. But to the extent that the ground starts to curve like this, that's geodesic torsion. So as I walk along and I start to lean to my side, right, that's geodesic torsion.
Okay, that makes sense actually, because the next part of the problem in the book says that if geodesic torsion is 0 everywhere, if and only if alpha is a line of curvature, which would mean that it's not.
Okay.
Right.
Yeah,
So,
keep consistent.
but
But anyway, this is a good example of a homework problem. It's not likely to be on the exam because it's, I don't know. I mean, it's a little, but you know, I'm not guaranteeing you. I mean, good, it's good to study it, but.
And then the last thing that I found online, seems like it might be true, but also I didn't know how to link it to this intuition, is that geodesic torsion can be considered like for every point in every direction, there's a geodesic that goes through that point in that direction, right?
Mhm.
And the geodesic torsion for a point is the torsion of that geodesic. But I don't know if that makes sense.
Is there a theorem that actually says that? Because it's not obvious to me.
I'll look it back to you.
Okay. But I mean, because I think there's the issue. Okay, when do these two frames coincide? See, like, I doubt there's going to be. I mean, it's hard to me imagine that these torsions are going to be the same unless the frames are the same, right?
Mhm.
And so, when would the frames be the same? Right. Well, I guess. Actually, now that you mention it, if the geodesic curvature is 0, right?
Mhm.
Then actually this u is in the direction of n. Right? So if geodesic curvature is 0, that term goes away, right?
Mhm.
Then
Oh,
the
yeah.
point is that u is the direction of t prime of s, right? And so actually the frames do coincide, right?
Mhm.
So if the geodesic curvature is 0, the two frames, the t n and b frame is equal to the t u and u cross t frame down here, right? So yeah, if the geodesic curvature is 0, then these are, they do coincide, exactly what you said.
Hmm.
Yeah. By the way, that could be a test question. Because that's, you know, short. You know, something that's reasonable to do in a small amount of time. Okay, other questions? Good questions. Yes.
Could we run through the intuition behind the first variation of area formula and like
Mhm.
the soap bubble problems that we described?
Sure, yeah, and that could be on the exam. I think I do have it on some practice exams, I think, right? So, I mean, okay, when you said intuition, right? I think of examples, right? And so, if I have a sphere of radius r, this is one of the simplest examples. Now, an even simpler example would be a plane where the mean curvature is 0, right? And we can I'll just point out that if you have a plane, right, the mean curvature equals 0. They use h for mean curvature, right? And if I flow it with, let's speed 1 up, right, then I just get another plane of exactly the same area, don't I? And so what we're trying to understand here is that a prime of t is equal to the integral over your surface, m. And the formula they use, is it like minus 2h times the speed eta? Is that what they say? Times the area formula. Is this the formula, how they write with their notation?
Let me confirm.
Yeah. I think they have a minus sign there, right?
They have u dot v.
Okay, even better. Is it minus 2?
It's minus outside of the integral, so same thing.
Okay.
2h u dot v dA.
2h. And then they have a dot product here?
Yes.
Oh, okay. U dot, and they use v or nu?
V.
It's a left.
Is like this? Okay, and v is the flow direction? Okay, I like it. I like it. Okay, good. Okay, so now what they're basically saying is So by the way, let me get, okay, mean curvature is, depends, okay. The sign of the mean curvature depends on the direction of u, right? So let's have, y'all, should we have u going out here? Okay. Now u's going out the same everywhere, right? So unit vector length 1, right? Okay. And then let's say that we are flowing out as well with speed 1, right? So we'll also have v go out with speed 1, the same everywhere, right? We'll have u equals v, okay? And in this case, the mean curvature is if the u is going out, then the mean curvature is going in, right? Well, sorry. The second derivative, you know, h is negative in this case, right? So in this case, that's what I meant to say, sorry. H is equal to negative 1 over r in this case when you have the unit vector going out. Am I correct? I think that was the conventions that we
Sounds right.
By the way, the reason I'm getting, there's something called the mean curvature vector, but I don't think the book ever talks about the mean curvature vector. Am I right? I don't think it ever does. And so this is incidental, you don't need to know it for the exam, but the mean curvature vector is equal to h times u. Okay? And in this case, for a sphere, it would be, you can see that it would be a vector pointing in. Okay? So, thinking of it as the mean curvature as a vector, you don't have to talk about what the sign is, because right now you have to say, well, it's minus 1 over r if u is pointing out, and it's plus 1 over r if u is pointing in, right? And but guess what? This hasn't changed. It's always the same. So mean curvature vector is a natural concept, but the book doesn't use it.
Comes up in chapter 8, apparently.
Okay.
As a mean curvature vector.
And by the way, if we do that, let's just go ahead and introduce that then, since you're saying it's in chapter 8. Then h times u is right there, right? And so then we have minus 2, and then we can just take the dot product of the h as a vector, right? Dot product v. Where I'll put the vector symbols in. And notice here that h without a vector and h with the vector symbol are two different things, okay? So yeah, you can see how the formula, it simplifies a little bit if we define h to equal h times u, okay? So it's a natural thing to do. Okay. And so in other words, the mean curvature vector is pointing in, right, in all cases. Okay. And now let's just see if this actually makes sense with this example we do with that v, right? And so what you get then is you get the integral over m of minus 2. I'll use this formula. H is minus 1 over r times then u dot v is just 1, right? dA. And so you're like, well, wait a second. What we get is a 2 over r and times 1, which is a changing thing. And then we're doing over area of 4 pi r squared. And so then what you get is 8 pi r. And you're like, well, is that the right answer? Well, and by the way, we're calling a prime of t, but guess what? T equals r, you could say, right? Because you're going at speed 1, right? So what's the derivative of 4 pi r squared? It's 8 pi r, right? Because the rate of change of r is 1, right? So r and t they're varying at the same speed, right? So that is in fact the correct answer. Does that make sense to everybody? So a sphere going out, if you increase the radius at speed 1, 4 pi r squared, right? ddr of 4 pi r squared is equal to 8 pi r on the one hand. And on the other hand, we can plug into this formula and we get the same answer if we flow out with speed 1 for v going out. Like that. So okay, so this is an example to keep in mind. The other example to keep in mind is, what if you just took a plane and we're flowing it straight up, right? If you flow the whole thing straight up, let's ignore the boundary, okay? That's a complicating factor. You can see the areas aren't changing at all, so it actually makes sense that the mean curvature is 0. Those are two cases where we can check and see that the answer, that this formula gives the right answer. Now, what's really cool about this formula is that there's no reason why your speed has to be constant. here we happen to be flowing out with speed 1 here and then speed 1 there. But what if we wanted to flow out just one side of the sphere but keep the other side fixed, make it an oval? Right? What's the rate of change of the area? Well, this just plug into your formula, it gives you an answer, right? So this formula is very useful, believe it or not. Now, they don't really have applications in the book, but if you want to see applications of this formula, just type into Google Hubert Bray thesis, right? And you'll see that I use this formula, I mean, a reasonable amount, because I was thinking about what if we put soap bubbles around black holes, right? And then that means they're going to have constant mean curvature. And so obviously, and then how does the area vary as I blow the bubble up and add more volume to the bubble? How does the area change, right? And that was the coolest idea in my entire thesis. And of course, I had to use this formula. And also, there's also something called the second variation of area formula, which is what is a double prime of t. I had to use that formula as well. And then, and of course, many other formulas. But this is the first formula that starts you in this whole discussion of understanding how areas of surfaces change as you move them. Yes?
So in the case of an oval, for example, or like a semi-sphere, like what exactly are we manipulating? Like the radius stays the same, but we just like half it? You just half everything when?
Well, okay. I mean, okay. You're trying to you want me to be more precise. I was thinking. See, the problem is the next simplest example gets a little bit complicated, right? Because like if I how else can I flow a sphere, right? I could take a sphere, and I was suggesting like let's not flow it in the southern hemisphere at all. Let's just flow it in the northern hemisphere, right?
Sure.
Then yeah, the rate of change of the area would be half as much. But then that sounds like it's going to detach, right? Like if I flow at speed 1 in the northern hemisphere and speed 0 there, right? But you know, okay, how about I smooth it out, right? So then I would get a larger sphere here, right? And then we'll just sort of meld it in like this, right? And if you did that, yeah, it's true, the rate of change would be half. The instantaneous rate of change at first would be half, right? Now, once you start putting in this weird stuff in here, that's going to affect things to some order, right? And so a double prime, that's going to be more complicated, right? It's not going to be the second derivative of this. It's not going to be 8 pi, right? It's going to be a more complicated thing. But yeah, but it actually will be half of this. If you did that, then the a prime of t at t equal to 0 at the as you just start doing it, it's going to be 4 pi, 8 pi r over 2. So that is true. If I were to show you, okay, let me show you actually what I think is a really cool second application. It's still decently theoretical. And it's called inverse mean curvature flow. This is a very cool topic. I won't go off too far into it, but inverse mean curvature flow. This is a real thing. And that's where you say, you know what, let's let the speed u, so let's use this notation here. Okay, now actually we have this vector v here, right? Okay, so let's, let v is the direction you're flowing, right? Let be the direction of the mean curvature vector. The negative of that divided by the length of the mean curvature squared. Okay, so if you plug in and say, well, what is that? Well, the minus the h, it's got this right here, right? So it's negative u divided by h. Okay, because this is h times u, and then one of the h's cancels, right? And let's suppose that we always do this for h positive, because we don't want to be dividing by 0, right? Then what's interesting is, if you plug into that formula, what is a prime of t? A prime of t then is equal to, and you might wonder, like, why do this? Well, physicists decided this was interesting, but the reason it's interesting is because of this formula here. Because then a prime of t is equal to the integral of negative 2h. Well, let's plug into this formula here. Okay, so just dot product with the h factor, I guess, right? So I get negative 2 actually, let's use the top. Let's use this formula. Let's use this formula. So I get negative 2h, and then u dot v. Now v is this, and so then I get another minus sign, so it becomes a plus, and then I get u dot u here divided by h, and then times dA. Well, guess what? U dot U is 1, H divided by H is 1, and so I just get 2, and then you're integrating, otherwise you're integrating 1 over the whole thing, and that's just called A of t, the area, right? So the rate of change of the area is the area. And why does that matter? Well, that's the first order ODE. You can solve that, and that means that A prime of, it means A of t, I can solve that ODE and say A of t is equal to some constant, whatever the area is at t equal to 0, times e to the 2t. So what this is saying is that areas are growing exponentially. Right? You actually have a precise control on the rate of change of the area when you make the mean curvature, when you do this inverse mean curvature flow. Inverse mean curvature flow goes, you have 1 over h here, right? And it turns out this is a parabolic flow, and so it actually has a short time existence theory, assuming smooth initial conditions. And the way to think of it is, let's just draw an example. If you have a sphere, by the way, it's just going to flow out and make it's going to preserve symmetry and just flow out in such a way that the areas are growing exponentially. Okay? But if you have something that's lumpy, let's say it's slightly lumpy, right? Wherever the mean curvature is smallest, it's going to flow out fastest, and wherever it's largest, it's going to flow out slower. And so it has a smoothing effect where it makes it more round. Does that make sense? And so this is one aspect of a parabolic flow is that it smooths things out. It's like the heat equation. It turns out it's in the same category of PDE as the heat equation. The heat equation is a PDE that, the heat equation, you may have seen it in your Math 353 or 356. And this is, if you have a function u, which is a function of t and x, y, and z, I'll just do t and x, then the equation is u sub t is equal to u x x. Right, this is the heat equation. And you solve that in 353 and 356. And what happens is no matter what the starting temperature is in the room, it sort of equalizes over time and approaches a constant. Right, it smooths out. And this smooths surfaces out. So it's a really cool geometric flow. And in the same way, you cannot run the heat equation backwards in time generically. You also cannot run this backwards in time generically. It has to flow out, smooths things out. You try to go the other way, it makes things less smooth and generally doesn't have an existence theory. And this geometric flow is quite famous, and in particular, some physicists suggested it to understand mass and general relativity in the 1970s. And it sat there sort of. No one knew what to really do with it because, on the one hand, it has these nice properties. It's smoothing and areas grow exponentially and it seems so natural. But the problem is, what do you mean inverse mean curvature flow? Because what if you have to assume the mean curvature is positive? What if the mean curvature, actually in my picture here, the mean curvature here actually looks a little negative, right? And so that means it's 0 somewhere. And how do you flow by 1 over 0, right? Like, how do you flow out with speed infinite? You know what I'm saying? It doesn't make any sense sometimes. And so physicists actually are literally the ones to notice that this had good properties, and then it took 20-something years for mathematicians to figure out how to make this precise. And it turns out it does exist, and it's beautiful, absolutely beautiful. Inverse mean curvature flow. It was made rigorous by Huska and Ilmanen. They announced their work in '96. It came out in a paper in 2001, and it's absolutely beautiful. Right? They demonstrate why mathematicians are useful, right? Is that this actually makes sense, right? There's a way to do it, and it's just to say it in words without getting into the technicalities. That they have to modify the flow ever so slightly. What you do is you flow by 1 over h, but you're always the surface is always asking itself a question, and that question is there a surface of equal or less area outside of me? And if there is, jump to that surface immediately. And so. That's how you maintain this. Is that if the mean curvature were ever negative, if the mean curvature is negative, that means if you flow out, then the area. Let's just give you all the basic intuition here, right? Is that if you have a surface where the mean curvature is let's say the mean curvature we think of it as, let's have u going in, okay? That's the way I think of it, I guess, in this notation. So here the mean curvature would be positive. And here the mean curvature is negative, right at this point. And so, and inverse mean curvature flow wants to grow the area exponentially, so it's going to go out here. Now here it's negative, but more importantly, if I were to do any flow, notice that the area is actually going down. Like I can actually decrease the area by flowing out this way. You'll see it has less area, not more area, right? And so the idea then is, I don't ever want to get to a situation where I have negative mean curvature, so how do I prevent that? I make sure I only consider surfaces that aren't enclosed by surfaces of equal or less area. This is the thing you can't allow. And so you simply say, look, if you're ever enclosed by a surface of equal or less area, then jump out to that surface immediately. Like we're not going to mess around with negative mean curvature stuff. Right? Turns out that's it. It solves the whole problem. Right? So you just say flow by inverse mean curvature flow, and at every point, if you're in a situation where there's a surface of equal or less area outside, you jump to that surface. And if you do that, what you actually do is you maintain this. Okay, I have to put it in quotes because that mean curvature could go to 0 just for a second. All right? Which this turns out to be the same thing as this. Okay, so you actually do get that. You can't have negative mean curvature because then if you flow it out, you would get less area. So anyway, that's. But yeah, examples are kind of hard, aren't they? Like I can do a sphere, I can do a plane, and then the next thing you know, I'm talking about theory, right? And that's why it's like hard to get too many more examples.
Why would you get less area?
Well, this a prime of t. This integrand has a sign, right? It's either positive or negative. And so if let's say v is always just flowing out, right? Then either this is positive or negative at each point. Where it's positive, that means the area is increasing. Where it's negative means the area is decreasing. And just to put it into picture form, when your surface is like this, when I flow out, the area is actually decreasing. When it's like, if you're at a positive mean curvature, as I flow out, I'm getting more area here, right? Like spheres are getting bigger, right? So the area is actually increasing as I do that, but it's decreasing if I were to flow smoothly out in this direction. And so if I let u be going in that convention, this is an example of positive mean curvature because areas are getting bigger as I go out. This is an example of negative mean curvature because areas are getting smaller as I go out. And so really, that gives you an intuition for what mean curvature is as well, which is, and that's actually a really nice way to think of it, is that mean curvature is simply the ratio of the rate of change of the area to the rate of change of the volume. Because if you compare these two formulas, so we put them side by side, these are formulas you're responsible for. I'll put it right under this one. V prime of t is equal to the integral of u dot v. Okay, so it's nice to look at these things side by side, okay? Notice it's exactly the same formula, but without the minus 2h. Okay, so I guess in this picture we're having, let's have u point out here. Right. And so in this convention, this minus 2h, right? So if I look at sort of at point-wise, right? This minus 2h, right? Which by the way is plus 2 over r in this picture, right? For a sphere. It's the ratio of this thing that you're integrating and that thing you're integrating, right? So if I take this integrand and divide by that integrand, right? It's minus 2h point-wise, right? So that minus 2h is telling you the relationship between the rate of change of the area locally and the rate of change of the volume locally. In fact, see, I can choose v to be anything I want. What if I chose v to be 0 everywhere, except v, let's suppose I chose v to be 0 everywhere except, right, and some sort of like a little bump function here, but otherwise v is 0, right? So v is 0 everywhere except a little bump function. If I were then to look at the ratio of a prime of t divided by v prime of t, then I'm going to get some sort of average of minus 2h in this vicinity, right? And so that's the very real sense in which the rate of change, the ratio between the rate of change of the area and the rate of change of the volume is minus 2h, if we have u pointing out. Does that make sense? So yeah, mean curvature, we first define it just to be the trace or the average of the principal curvatures, which by the way is twice the trace of the shape operator, right? That's a definition, that's for formulas, but what is it geometrically? It's really this formula tells you what it is geometrically. It tells you how areas change, right? As you flow out. Other questions about this? Okay, other questions I'd like to hear about for the final exam? We've talked about the Gauss-Bonnet formula. That's super important. Mean curvature is another major topic, so that was a good question. Shape operator, make sure you know all that stuff. Of course, you had the first exam on that, right? You got did pretty well on that. Let's see. Other practice problems y'all saw that you might have questions with? I mean, here's sort of like there's a collection of problems there. They're kind of a little bit interesting. So let me give you an example of interesting thing that I could conceivably put on the exam. Let me show you what the Gauss-Bonnet theorem is for two-dimensional black holes. Okay, this is a kind of fun topic that I love putting problems like this on there. I've never put this particular problem on there, but who knows? Maybe I will. But let me just give you a flavor, right? And that is, let's suppose, I've been thinking about this for a while. So let's suppose, suppose you have a cone, right? Now, why am I choosing a cone here? A cone has zero Gauss curvature, right? Except at the vertex here, right there, it's not defined. So what I want to do is, so we'll say it's a cone, right? And then what I want to do is I want to erase this, okay? And so outside of some radius, we'll have something that's a cone, okay? And then otherwise, what I want to do is I'm going to put in a some minimal surfaces like this. Well, they're actually I call them minimal surfaces. They're minimal curves, right? So I want to have zero geodesic curvature boundaries there. The geodesic curvature of the boundary equals 0 here, and the geodesic curvature of the boundary equals 0 here. Okay? Now, what I'm going to do is I'm going to let you all see inside the test taker's mind. Okay? I'm going to create a problem that I could put on the final exam. Okay? Because all I'm going to do is write down. Now, by the way, the Gauss curvature is 0 in this cone area, isn't it? Right. But otherwise, let's not make any assumptions about the Gauss curvature. Right. Gauss curvature, K could be anything. Could be positive or negative. Okay. In this interior region. Okay. Could be positive or negative. And so, what does the Gauss-Bonnet theorem tell me? It tells me that the integral. Let's call this whole thing M, right? And this is actually where I have to be a little bit careful. Okay, let's actually, because the problem is I'm tempted to play the Gauss-Bonnet theorem to this whole thing, right? But you can't really do that, right? So let's, because the Gauss-Bonnet theorem applies to a finite surface. So let's go out. Let's call this this thing I've drawn here. Let's call this everything on the inside. Let's call this a circle at radius r. R is kind of a little bit arbitrary. And we'll call this m sub r as everything on this side of c sub r, okay? So let's take the integral over m sub r, okay? And let's look at k dA plus the integral over the boundary of m sub r of the geodesic curvature ds. Now we know that this is equal to 2 pi times the Euler characteristic of m sub r, right? Have I done it right? That's our Gauss-Bonnet formula. And now I'm going to apply it to this particular setting. Now, what is the Euler characteristic? Well, if we don't have, by the way, I'm already going to tell you that we're going to call these black holes. Okay, we're going to call these two-dimensional black holes. Okay. This will make the problem interesting. Get everyone's attention, right? And it's actually true, by the way. In higher dimensions, black holes are things that have zero mean curvature. Right, so if you up the dimension here by 1, notice this is a two-dimensional surface here, right? But if you up the dimension by 1, it's a three-dimensional slice of a space-time, then you have zero mean curvature things, and then we call those apparent horizons of black holes. Okay, so I'm doing everything one dimension lower, so it's reasonable to call these, we have two black holes. And so let's let n, I haven't used n yet, right? N, let's let that equal the number of black holes, okay? In fact, I could do n sub bh, right? Number of black holes. Okay. Then the Euler characteristic, if there were 0 black holes, then it would be a disk, and the Euler characteristic would be 1, right? But because I had to take out 2 phases in this case, I'm going to have to subtract off n's of black holes. Every time I add a black hole, it decreases the Euler characteristic by 1. Fair enough? Yes.
Why is everything below MR a disk? Or are you only focusing on?
If I were to, okay, let's make that an assumption. Okay, I'm going to assume that if there were no black holes, like in other words, if I fill this in and I fill this in, that this is topologically a disk. Okay, I'm going to make that an assumption. Okay, so it's as drawn.
Okay.
Okay. Yeah, because you might wonder, why couldn't there be? That's a good question. Why couldn't there be some topology somewhere, right? Let's not do that.
Oh, yeah, I was going to assume it was a sphere topologically. Those two things were closed up. Like
Well, yeah. If you close this up here, it is a sphere, right? So yeah, I mean, if you were to put a disk in right here and put a disk in here and here, so in other words, it really is. It's 2 minus 3, right? I mean, the point is, it's either you can either think of it as 1 minus 2, or you can think of it as 2 minus 3. You get the same answer, right? A disk has Euler characteristic 1. A sphere has Euler characteristic 2.
Okay.
But I'm just remembering the fact that a disk has Euler characteristic 1, right? And that's everything inside here, not filling in there. And then I take away those 2 black hole areas, those 2 faces, right? And so I got to decrease the Euler characteristic by that much. Okay, so now the integral of what is this? Well, this left-hand term is the same thing as the integral of over the whole manifold of k dA. Why? Because outside this, it's already in the cone area here. K is 0 out there anyway, right? So I could just say just integrate k over the whole manifold. And now, what is the integral over the boundary of the geodesic curvature? Well, the geodesic curvature is 0 there and 0 there by given. It's by the problem. It says the geodesic curvature is 0 there, so I don't get any contribution from the boundary here. But I do get a contribution from the geodesic curvature up here, don't I? Okay, and so I get plus the integral over the this circle radius r. I mean, it's a little bit arbitrary. We call it circle radius r. Some large circle, right? It's kind of like a circle radius r. As r gets bigger, it's supposed to get further out, okay? Times the geodesic curvature ds. And then this equals 2 pi times this, right? 1 minus the number of black holes. Okay. You guys ready? And now what I want to do is I'm going to take this 2 pi here. I'm going to split this up. And one of the 2 pi's I'm going to leave over here, and the other black holes I'll move over there. I'm going to put 2 pi minus the integral over a circle radius r, the geodesic curvature ds. And then over here, I'm going to say the integral over m of k dA, and then plus 2 pi times the number of black holes. And that equals this. You guys agree with my calculation so far? And now I'm going to just do some definitions. I'm going to call this matter density. I'm going to call the 2 pi is the mass of a black hole. All black holes have mass 2 pi. Okay? And I'm going to call this the total mass of the system. Okay? And so now you've seen behind the curtain. Let me tell you what the problem is I would give you. The problem I'd give you is, suppose you have a setting like this. Suppose we define the total mass of the system to be this. Suppose we define the mass of a black hole to always be exactly 2 pi. And suppose we define define k to be the matter density in this system. Prove that the integral of the matter density plus the mass of the black holes equals the total mass of the system. Okay. Turns out this is a perfect analogy to what actually is true when you go up 1 dimension. Okay, this is actually not just nonsense. This is what the mass of black holes are, and this is what matter density is in 2 + 1 dimensions, right? if the universe were 2 plus 1 dimensional instead of 3 to plus 1 dimensional, Gauss curvature of each slice would be what matter density is. Each black hole would have a mass of 2 pi. And this is how you measure the total mass of the system. And the total mass of the system does equal the sum of the integral of the energy densities plus the mass of the black holes. Now, actually, by the way, in higher dimensions, unfortunately, it's way more complicated than this. See how we can prove this in like 3 lines?
Yeah.
It turns out the Gauss-Bonnet theorem isn't true. It's a much more complicated question. We can't just quote the Gauss-Bonnet theorem in 3 dimensions. So this was a very hard problem to figure out.
This is why there's like a diverse range of masses of black holes. 'Cause black holes aren't all the same mass, right?
Yeah, it's like, why is mass? Yeah, exactly. Well, yeah. So, for example, just to finish the thought, if in higher dimensions you can have the same picture, but imagine now this is a 3 manifold, right? Then what is true is that the total mass of the system, right, that would be the rightmost term. It's true that it is greater than or equal to the square root of A over 16 pi, where A is the total area of these H equals 0 black hole surfaces. So where a black hole is, and that's assuming, by the way, assuming that you have non-negative scalar curvature in your space-time, and that's kind of like energy density. So remember, scalar curvature is a number at each point. It's the full trace of the Riemann curvature tensor, so it's kind of analogous to Gauss curvature. So you can see if K is greater than or equal to 0, then you get that the total mass is greater than or equal to the mass of the black holes, right? And same thing is true over here. If you have non-negative scalar curvature, then the total mass of the system is greater than or equal to the mass of the black holes. Here's the problem. I wish I could write a formula down like this, and you can, but it gets more complicated. It's actually, so I'll just write this. Okay. In other words, if you want to get more of an equality, you can try, but it's not. Let's put it this way. This does not equal. It's not equal to that plus the integral of the scalar curvature. By the way, you got to divide by 16 pi to get energy density. That's all. dV. So that would be energy density. Turns out, when you take the integral of the energy density and add up to the mass of the black holes, that doesn't give you the total mass of the system. It's a more complicated relationship. And in particular, it would appear that you need to multiply this by something I might call Q. It's like a potential energy term. It goes between 0 and 1. And then you can get stuff where it's approximately equal to this. So I think actually there are a couple of theorems where you can write something along these lines. But then Q is between 0 and 1. And so it's a bit of a complicated relationship, actually, right? And that's at the edge of what's known right now. So I'm giving you, what I figured out in my career, and then also stuff in the last few years. Yes.
I have a question kind of related to that inequality. The total mass of the system can't be has to be equal to or greater than the mass of the black holes, right? So does that mean if geodesic curvature is non-zero, it has to be negative? I mean, I know this is just like an analogy, but for the right hand side.
Great. Yeah, I think you've observed something nice, right? So you're talking about this right here?
The right hand side and
Yeah.
the cameras.
So this is positive, right? Is that what you were saying?
Does it not have to be, if there exists even one black hole in the system and we've defined it to have a mass of 2 pi, then the right hand side can't be less than 2 pi?
Yes. So let me tell you what you figured out, and I'm glad you pointed it out. It's very astute. Is that unlike 3 dimensions, there's another difference with 2 dimensions, and that is there's no way to draw this picture where K is positive everywhere. I actually have to have some negative K. You have to have negative energy density, right, to draw this picture. So if I make this positive, right, and then you can see that, well, this is less than 2 pi, right? And so that means I can't have any black holes. So the point is that if I want to have black holes, then K can't be positive. And that is kind of annoying, actually, right? So I have to, because I want to be able to show you all black holes, because that's cool, right? But then to get that to work in lower dimensions, I have to allow there to be K to be negative, which is fine until I tell you K is energy density, and you're like, whoa, I didn't realize energy density could be negative. And actually, we've never observed negative energy density in the universe, although technically it's not prohibited by general relativity. It's not prohibited, it's just that's an experimental fact. We've never detected any negative matter density. Yeah, so you're absolutely right. But nevertheless, I mean, this statement is true, and so that would be an example of kind of a cool exercise I could put on the final exam. So I would understand that, right? Now another question you might have is, why would you call this total mass? One thing I'll point out is that this quantity here is actually invariant on R. As long as R is in the cone region, if as I move the curve out, then this thing doesn't change. And that could be a test question. You know, prove that 2 pi minus the integral of geodesic curvature around these circles of radius R out in a cone is the same no matter which curve I choose. Right? And that also uses the Gauss-Bonnet formula to prove. I'll give you a little quick sketch of it. If you look at a cone, right? And then here's one circle on the cone, and here's another circle on the cone, right? And now we look at this sort of annular region here between the two circles. Let's call this C1, call that C2, okay? And now here's the key point about cone, is that it has Gauss curvature equals to 0, right? And so when I write down the Gauss-Bonnet formula, right, integral of k dA plus the integral of over m, over the annular region, we'll call it A, right? And this is the boundary of A, of the geodesic curvature ds. This equals 2 pi times the Euler characteristic of an annulus, which is 0, right? Right? Because a disk is 1, you take out a face, 1 minus 1 is 0. So an annular region, that sort of strip, right? And the Euler characteristic 0, right? So this is 0. And then well, wait a second, but this is also 0, right? And so what you have then is that the integral around the boundary of the annular region of the geodesic curvature ds is always equal to 0, right? And yeah, and so then what you get then is the integral of the geodesic over C2 and also the integral over C1 of the geodesic curvature ds plus integral of the geodesic curvature ds around C2. This equals 0. Now keep in mind, this is the convention here is that geodesic curvature is the geodesic curvature here is positive, but the geodesic curvature here is negative. Why? Because it's referring to curving towards the surface or away from the surface, right? So you get an opposite sign here, right? So if we use the convention where we think of this, the C1 as the boundary of this, right? Then it would flip the sign on the geodesic curvature. And so therefore the integral of the geodesic curvature here equals, I can put it to the other side without a minus sign, equals the integral of the geodesic curvature here, where they're both the boundary of, on things below them. And so in other words, this term here doesn't depend on radius r. So that's a sketch of it for you. Does that make sense? Any questions? Yeah, I mean, that was a subtlety here, which is when we write down the Gauss-Bonnet formula, geodesic curvature, just to be clear, if you have a disk like this, right, and you're taking the boundary of this region here, the geodesic curvature is negative when it's curving away from the surface, and the geodesic curvature is assumed to be positive when it's curving towards the surface. Okay, that's the convention for geodesic curvature. And so, whether you're taking the boundary of the annular region or this cone down here, right, makes a difference. Okay, just up to a sign. Yes?
You just addressed the last part. I was going to say it's up to a sign, though, depending on
No, the geodesic curvature is always uniquely defined for the Gauss-Bonnet formula. It's positive if it's curving towards A, or the region in question, and it's negative if it's curving away from A.
Okay.
Yeah. But my key point is this C1 the boundary of this annular region, or is it the boundary of this cone region below it, right? Well, it's both.
So it can.
But the geodesic curvature, when you measure it with respect to this annular region, will be the negative of when you do it with respect to the cone region below it.
Awesome.
Yeah. And so actually, the Gauss-Bonnet theorem can be used to show that this is invariant. So that could also be a test question. Right. So these are the cool applications of the Gauss-Bonnet theorem, which I like for sort of near the end of the exam when you've gotten them all and you're like starting to feel disrespected, right? And you're like, this was too easy, right? Like, come on, challenge me, right? And then I'm like, okay, well, let's just go, get into, let's do applications of the Gauss-Bonnet theorem, right? Then this is the kind of thing that I like. Because actually, it's not hard. It's just putting you into a different environment, right? Where it's like, oh, okay, application. I haven't done that yet. Okay. How does that work exactly? Right? How do I apply it? We got one more minute left. Any other questions? I mean, I think you all sound like you're pretty well prepared. You're asking the right questions. Should we even have a final? Should we just blow it off?
Let's skip it.
Skip it?
Yeah.
Should we take a vote? Who wants to have a final? Raise your hand if you'd like to have a final. Okay, you got one vote.
What are the grades?
Everyone else just say skip it?
Yeah.
Because at this point, you've either learned it or not learned it to a considerable extent. You know what? I think we got to go ahead and have it. All right? I think we got to do it. All right? It just sort of looks better.
I thought you were about to drop a bomb on us.
You know what? I mean, it's kind of funny. Like, grading exams and stuff like that, I'm pretty sure it's like, I don't enjoy this at all, okay? Writing exams is a hassle. Grading exams is a hassle. But actually, I think at the end of it, it's very satisfying when you study for it. You get really well prepared. You do well, right? And it gives you that good feeling, right? So I would be robbing you of that, right? If we didn't have the final exam. So anyway, I hope you all really enjoy preparing for it and get ready for it. Do well. Have a good feeling after the end of it, right? And more importantly, I hope you guys really enjoyed the class. That you enjoyed learning some differential geometry, and that you see how fascinating it is. And I hope it's been a pleasant experience, and that you continued, that it's enhanced your love of mathematics and science in general. So, thank you guys.
Thank you.
Stay in touch. See you for the final.